Hello everyone. Today I'm going to talk to you about the Michael reaction. And the reaction is named after Professor Michael. That's his last name. So Michael reaction basically is a type of reaction that a nucleophile, you have a nucleophile that attacks the beta position of an alpha-beta unsaturated ketone or an alpha-beta unsaturated aldehyde. So the compound that we're using in the lab today is chalcone, or benzyl acetylphenone. So we have remember, these are designations for the phenyl group, right? So we have this compound, which is going to react with aniline. So this is chalcone. And that is aniline. And as I said before, the reaction involves nucleophilic attack onto an alpha beta unsaturated ketone. And the position where the nucleophile attacks is the beta position. And that's because the beta position, it's where the carbon is partially positive, right? Just think about this. You've got this conjugated system of alpha beta unsaturated ketone. The carbonyl group is electron pulling, right? So if I were to show you kind of a resonance structure, which is, I'm going to exaggerate and place the positive charge on this carbon by pulling the pi bond away, forming the carbon-carbon double bond, and then pushing the pi bonds on the carbonyl onto the oxygen, right? So you can see that this carbon is really the carbon that is positive, right? And that's where the nucleophile attacks. Of course, I said this is exaggerating, but if I were to really show you the true structure would be having a partial positive on this carbon and a partial negative on the oxygen, and partial pi bonding between carbon, 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 oxygen, right? So again, you can see that because this carbon is partially positive, that's where the nucleophile is going to attack. Okay, so this was just like an intro. So after the nucleophilic attack, you get this intermediate, right? So the lone pair on the nitrogen attacks the beta carbon, pi bond gets pushed over here, this other pi bond gets pushed over onto the oxygen, right? So of course this O minus will immediately going to take away a proton from this ammonium salt. and you form what is known as the enol. By now you will have learned that enols are tautomeric to ketones, so basically this thing converts to the corresponding ketone. And if you were to show with arrow pushing, this is becoming a carbonyl, and this is picking up the proton, okay? So we end up with our product. So this is our product. Now, one thing to mention here is that, you know, when you study the nucleophilic addition reaction to the carbonyl, which is probably where you are at this stage in lecture, that's also where you learn about the Michael reaction, right? So there's also a possibility that the amine can attack the carbonyl, right? In which case you form an amine. But there are some bases and nucleophiles that actually have their own characteristics. Generally speaking, when the nucleophile is a weak base, okay, then the attack takes place, and I'm talking about a system where you have an alpha beta unsaturated ketone as the starting material, right? When the nucleophile is a weak base, the attack takes place in the fashion of Michael, which is attacking the beta position. If the nucleophile is a strong base, right, then you get predominantly attack to the carbonyl, right, of the ketone. You'll still get some attack at the beta position, even in the case of a strong nucleophile, strong base, good nucleophile, right? But primarily, you know, the attack takes place at the carbonyl if you have a strong base and a good nucleophile, right? But in this case, aniline happens to be a weaker base than, let's say, if we were to compare this with, let's say, methylamine. Let's say if we were to do the reaction with methylamine instead of aniline, you would expect quite a bit of attack of this amino group onto the carbonyl than the beta position, because this is a stronger base compared to that of aniline, okay? So weak base or weaker bases attack the beta position, and that's how Michael reaction was discovered, okay? There are other weak bases. If you have, let's say, if you were to treat this with sodium cyanide, let's say if our nucleophile was cyanide, which happens to be a superb nucleophile, but it's also an exceedingly weak base, right? So what would you expect in the, you know, if the reaction involved sodium cyanide? You would expect exactly the same thing, that the cyanide would attack the beta position of an alpha beta unsaturated ketone. So to recap this, you know, when you have a weak base, good nucleophile, the attack takes place in the beta position of an alpha beta unsaturated ketone. If you have a good nucleophile, which is also a strong base, right, the attack takes place primarily at the carbonyl, okay? So, so with aniline, we said that the attack takes place in the beta position, and you enolize this, right? You get the enolate ion first, which then picks up a proton to turn into enol, and then the enol turns into a ketone. This is known as the enol-keto tautomerism. Enol-keto tautomerism. And if you look closely, I have an equilibrium here, but most of the compound is going to become a ketone, and some of it is in the form of an enol, right? So the equilibrium really lies on the side of the ketone than the enol. There are situations where the enol is actually more stable than ketone, but that's beyond the scope of this discussion today, okay? And that's pretty much wraps up today's experiment. And then, of course, since you use 1 gram of chalcone and then 1 ml of aniline, you have to determine which one is the limiting reagent in order to calculate the percentage yield, right? So whichever one is the limiting reagent is going to be the one that you're going to use as the number of moles that you would expect to be formed in the product, okay? So I think I'm going to show you how to set up the reaction, and we'll continue a little bit later on. Hi everyone, so today we're going to do the MICO reaction involving the reaction of trans-benzyl acetophenone, or commonly known as chalcone, and treated with aniline, and I'm going to describe to you the techniques that are involved. So your procedure calls for measuring 1 gram of chalcone as the starting material. It's exactly 1 gram. So I'm going to transfer this to a 25 milliliter round bottom flask. Then I'm going to dissolve the chalcone in 5 milliliters of ethanol. So we're going to measure 5 milliliters of dry ethanol. Perfect. So that will dissolve or should dissolve most of the chalcone. Doesn't have to all go into solution, but of course on heating it will. And now we will add the 1 milliliter of aniline. So now we're going to add 1 milliliter of aniline, and I'm measuring it using a graduated cylinder, 10 ml graduated cylinder, and a glass disposable pipette. So I have exactly 1 ml in here. And add it to the chalcone dissolved in ethanol. Okay, so we are now ready to do our reflux. This reaction has to reflux for an hour, but before doing that, I'm going to add a few boiling chips. To have a smooth rate of reflux, and put a little bit of grease. You know, the greasing technique is important, that you don't put too much grease, just enough at the very top of the mel joint, okay, so that when placed inside the round bottom flask, it can move around very easily, right? Okay, so I'm gonna make sure that this thing is sitting inside this heating mantle properly. So I'll put this jack so that I can raise this up, or I can lower this. And then put the water tubing in and out. In from the bottom, out from the top. And the reason for that is you want the coldest part of the water to be over here, because when the solution starts to reflux, you want it to reflux at the coldest place, which is down here, not up there, right? So I'll open the water slowly. And I'm ready to start heating this thing. Remember, nothing should be at the top here. It should be open to air. So because this tiny flask is a 25 milliliter flask, and my heating mantle is much larger, I can simply add some aluminum foil around this. So I can put some aluminum foil around it to keep the heat kind of uniform. And you let this go. Make sure that the rate of reflux is 1 drop a second. I'm not there yet, but I'll show you when that happens. So this has to reflux for an hour before the reaction completes. Okay, you can see that this has now been refluxing for 1 hour, and you can see the rate of reflux is at a very nice rate. It's like 1 drop a second. And we're going to stop it, let it cool, and allow the crystals to show up. Okay, so we just finished the 1 hour reflux of the Michael reaction, and the crystals are very nicely forming, and want to make sure you can see it. Okay, so I'm going to retrieve this crystal and filter it using this vacuum filtration. So first thing, you have to remove the condenser. I already cut off the water source. You know, because I have put some grease over here, I can just wipe off that grease using some paper towel. This way the compound does not get contaminated with grease. Okay, so I can now swirl it up to maximize crystallization. I'm ready for vacuum filtration. So keep swirling this like that quickly and pour it out. So while this is getting dry, you can see there's still some crystals in here. which I'm going to wash using the same solvent that I used to make this Michael adduct. And that was ethanol, right? So, except that I need to use a little cold ethanol because I don't want to really redissolve this solid, right? So here's some cold ethanol. Not too much, just a little bit. So that you can transfer all the crystals. And you can see this thing is getting dried. Wait until no more ethanol is getting sucked out. In the meantime, I added some boiling chips in there, which I can kind of fish out. Okay. So this thing is becoming nice and dry. And I'm going to try to put it on a grain paper. You know, when you finish with the vacuum filtration, never try to close the water first. Always disconnect the vacuum line and then close the water. Because if you do it the other way, water can get into the system and contaminate your product. So here we have the final product. And I'm going to pre-weigh the paper and tear weigh it. It's reading 0. Now I can you see there is crystals that are still stuck to the paper, so I'll just take this out, the whole thing, with the paper. There's always a little bit of loss which you cannot avoid, right? That's the human error. And from the paper we can scrape the compounds out. You can see it's relatively dry. It's not completely dry. So once we'll leave it on the bench on the paper for maybe 5-10 minutes, all the ethanol is going to evaporate. Because right now, if you wait it, it's gonna, the yield is gonna be high. So give it about, I would say 10 or 15 minutes. And if you want, you can leave it, in your drawer for the following week, and it will certainly be dry. Okay? So, and then you get the final weight, and you calculate the yield. Of course, the procedure also calls out for determination of the melting point, and that is, you have to do this when this is completely dry, and this way you can identify that the compound you made is in fact the Michael adduct. Okay? So hope you had a good time watching this video, and good luck.